Alrighty guys, here we go. We're going to be looking at normal distributions today. Now, you already know a lot about this. If not, then I suggest you go back and look at some of the stuff that we did last year during the core. I got a couple other videos about it. You're welcome to go back and look at those if you need to, or your textbook is fine. But right now, I just want to do a quick review and then go into a couple of other ideas that will be helpful as we're looking at normal distributions. The first thing is just remember the normal distribution looks something like this, often referred to as the bell curve. You've got your average, which is right in the middle, and then it's symmetric about that average. Now, we often talked about the standard deviation, and we said that if you go a standard deviation away, then you have a certain amount of data, so that's mu plus sigma, which is standard deviation, and then on this side you had mu minus sigma, which was the same distance away. Now, we pointed out that each of these was approximately 34%, okay, which meant that the amount of data within one standard deviation was about 68%. Now, that's not exact, it's just an estimation. We then went and said, okay, well, if we go 2 standard deviations out, that's approximately 95%. And then if you wanted to go one further standard deviation, that would be a total of 99.7% of the data. Now, we should recognize that the domain for this is all real numbers. Now, given that, we also recognize that outside of 3 standard deviations is only 0.3%. And so in a lot of realistic situations, once we've gone more than 3 standard deviations out, we may kind of ignore anything out there. It's often common that if you're dealing with something real like heights or something, that you're not going to be able to have negatives. Understand that the function itself does actually have those values, but we may not consider those. Now, just as a reminder, the function, which we don't actually use very often, but there is a function for this specific curve, is 1 over sigma square root of 2 pi e to the negative, and you can see why we don't use it very often, because it's quite annoying, x minus mu over sigma squared. Okay, and so that's the formula that would give us these specific values, so that we have a probability density function, just like we have for the other types of functions that we've looked at so far in this option. Okay, the other thing that we should remember is that this is a normal distribution. We do have what's called the standard normal distribution, and then the standard normal distribution is this. But in this situation, for the standard normal distribution, mu is 0 and the standard deviation is 1. Okay, now what that allows us to do is create what we call the standard normal random variable, which we define as z. Now, z is the standard variable for any specific value. If I have a specific value, a specific random variable for a normal distribution, if I take that and I subtract the average and then divide by the standard deviation, then it gives me a standard normal random variable. Okay, that's the z-score, which we talked about in our units before. And the idea, of course, behind that is that it takes it back to kind of this parent function, the standard normal curve. And with that information, we kind of have a specific place where 1 is 1 standard normal deviation. What the z is how many standard deviations is my value from the middle, right? So if you take that value, subtract the average, you get a number, and you divide that by the standard deviation to show how many of those standard deviations this value is. If you're to the left of the mean, then you're going to get a negative. If you're to the right of the mean, then you're going to get a positive z-score. Okay, so now that having been done, let's just do one review question real quick, just to refresh our brains and remind ourselves what we're doing here. So I've got a standard normal curve. I've got a value right here of 13 and a value right here of 36. The area up above this is 0.1356. The area down below this one is 0.1150. 0, 6. And what we want to do, of course, is find the mean and the standard deviation. Okay, so what we can do, unfortunately, we don't have those, so we can't use, on our calculator, we can't use the norm CDF, because we need both of those numbers in order to be able to do that. But what we can do is we can start with this specific value, and we can find the z-score that's associated with this probability. Remember, inverse norm on your calculator allows you to put in an area, probability, and then it allows you to find the z-score, the standard normal random variable, associated with that area. Okay, so that's what we're going to do. We're going to call up our calculator. And so on our calculator, what we're going to do is we're going to go into distribution, and we'll go to inverse norm, which is number 3. And so the area, I'm going to start with this one, the 0.11506. And for the standard normal, it's 0, 1 for the mean and standard deviation. And so we can then paste and get our answer, which is negative 1.2. So for this one, the z-score equals negative 1.2. And then we'll do the other one. Now recognize that on the other one, our area is up there above. It's above, and the area that this is asking for when we do inverse norm there is the area below, right? Whenever we do a cumulative distribution function, it's always considering the values below it. So what we'll do here is for our area, we'll go 1 minus 0.13566. And so that'll give me everything below. Remember, this is a probability density function, which means that everything is adding up to 1, 100%. And then again, I've got the 0 and the 1, and I then get the z-score for this one, which will be 1.1. Okay, now with this, knowing the z-score, I can now use this, z equals x minus mu over sigma, and so I can go negative 1.2 equals this value, 13 minus mu over sigma, and I've got a second one, which is 1.1 equals the 36 minus mu over sigma. And then at this point, you really just need to be able to solve. One way to do it would be to multiply by sigma divided by 1.2, so then I'd have 13 minus mu over negative 1.2, and then I'd have 36 minus mu over 1.1, and then you could solve this on your calculator. Okay, so when you do that, you could graph it, make it y equals. You can also use this you could do some type of simultaneous equations or row reductions or something. But from that point, I think you're probably okay solving a simultaneous equation. You can set them equal to each other, right, since the sigmas are substitution, whatever you want. But hopefully when you work that out, you end up getting that sigma equals 10, and the average is 25. All right? So that's enough of a review. Let's get on to kind of the new stuff. What I want to look at today is kind of neat. Think for a minute of the binomial distribution, right? Binomial distribution has something to do with Pascal's triangle, right? And Pascal's triangle affects how many of each specific binomial occur, right? Now, the ones on the ends are less common than the binomials in the middle, right? And you've seen this before when you expand a binomial or whatever. The coefficient is bigger in the middle because of this. Now, what you may or may not have noticed, of course it is symmetrical. Let me just post up here an example of n to the 10th, all right? So this is 10 repetitions of something, probability of 0.5. This is the distribution, right? And what we've done in this graph is we've said, okay, well, let's add up how many total coefficients there are and then divide each one to find out what percentage is at each one. The nice thing about that is that all of these rectangles then add up to 100%, which therefore is a probability distribution function. Okay, so now with this, do you recognize what this looks like? It looks an awful lot like a bell curve. And in truth, it's actually very, very, very close to the bell curve. As a general rule of thumb, if n times p is greater than 5, and n times q is also greater than 5, then we can approximate the binomial distribution using a normal curve. Now, that's pretty snazzy. I don't know if you recognize how cool that is, but it's actually, I'll show you an example here in a minute, but one thing you need to recognize is that, you know, on your, for example, on your calculator, the only one that can go backwards is the normal curve. Everything else, you have to have the numbers that you need and then put them in, and then you'll be able to work it out. The only one that you can actually put in an area and then get the number out is with the normal curve. Now, we do have to make a couple of small adjustments. Okay, we need to recognize that, for example, right here is the value of 2. It actually goes from 1.5 up to 2.5, right? And so, for example, if the binomial distribution was requesting the probability of getting a 2, then if we were approximating using the normal curve, we would actually find the probability from 1.5 up to 2.5, including the 1.5, not including the 2.5 as possible. Remember, for a continuous distribution like the normal curve, the probability of one specific event occurring is negligible. And so what we actually need is the range of those probabilities. And notice on the left-hand side it'll go over a little bit, on the right-hand side it'll go under a little bit. I didn't draw my curve very well, but the curve should go through the center of each of these. And that, then you can see over here a little bit of overlap, a little bit of underlap. And that therefore gives us a fairly good distribution. Here, you want to see? Well, let's just kind of wrap this up, and then I'll show you an example. Okay, so therefore, if we have a binomial distribution, so our random variable is binomial with n and p, we can then approximate. If this is the case, then we can do a continuous distribution using a normal curve. And remember, the normal curve needs the mean and the standard deviation. Now remember, sorry, not standard deviation, variance, right? So the mean is NP for binomial, and the variance is NPQ, but since I'm in terms of NP, then I'll just go 1 minus P for Q. And so I can actually use this to estimate that. Let's check it out. Let's look at an example so you can see. All right, there we go. We're going to consider the binomial random variable B15.4. Now notice that if I go 15 times 0.4, that's P n times P, I get 6. And if I do 15 times 0.6, which is n times Q, then I get 9. And so in both situations, it's greater than 5, which fits our restrictions up here. They both need to be bigger than 5. And so let's go ahead and have a glance and see how it works. So first we're going to find the expected value of x. Now remember, the expected value of x is simply np. So n times p we just did, which will be 15 times 0.4, because this is n, this is p. And so I get 6. Remember, variance is just NPQ, so that would be NP, which is 6, times Q, which is 0.6, which will then give me a value of 3.6. All right, now using our calculator, we can find these specific probabilities. So the probability that x will be less than or equal to 7. So we're going to go into our distribution, and we will go down to binom CDF. Okay, which is letter B there. Oops, I went a little bit far. Okay, so binom CDF. My trials will be 15. The probability will be 0.4. And the x value will be 7, and this will give me everything from 7 down. And I get 0.787. Okay, now if I want to get the probability between 3 and 12, then I'm going to have to do the probability of 12 and then subtract the probability of 3, right? Well, less than or equal to 12, and then the probability of less than or equal to 3, because essentially what I'm doing is I'm taking the 12, which is all of this, and then subtracting the 3, which is that, and that will give me between 3 and 12. Okay, so that's what I want. So we're going to do the same thing, and we'll just second entry so that we can change that to 12. And then we will go minus the same thing, which will just go into distribution again, and there we go, 15, 4, 3, and we then get our final answer of 0.909. Oh, sorry, that is not correct. I lied. Yes, I hope you caught that. This needs to be 2, because if I want to include the 3, then I actually want 3 there. I want 2 and below not to be there. Sorry. So 0.972. Yeah, so if I want to include 3, then I need to go from 2 below. Okay, because that's discrete. Okay, so 0.973 is the probability that's between 3 and 12. So now, if we consider this to be a normal distribution, so let's make the approximation. So we'll go in. My mean will be 6. My variance will be 3.6. So that is x. That's our approximation. And so to find this same value, x being less than or equal to 7, remember we want to do everything up to 7.5, and so that's why it's asking for this. And so we'll do now the inverse, the norm CDF, and we'll go everywhere from negative 1e99 all the way up to 7.5. Our mean being 6, and our standard deviation, standard deviation is the square root of 3.6. Remember, 3.6 is our variance. And so I push enter, and what do I get? Holy smokes, I get 0.785, which is pretty dang close to the 0.787 that I came up with up there. Okay, we can do the same thing for the 3 to 12. Now this time, remember, for 3, I can actually, remember normal distribution, this is going to be a little bit easier. Normal distribution, if I do the normal CDF, it actually lets me choose a lower bound and an upper bound. So if I want to go from 3 up to 12, then I'm going to start at 2.5. So I'll go 2.5, and then I'm going to go up to 12.5, because 3 will include 2.5 up to 3.5, and then 12 will go from 11.5 up to 12.5. I'll leave the mean and the standard deviation the way they are, and let's see what we get. 0.967, which is close, but not as close as obviously this other one was, but that's still pretty dang good. That's 0.006. That's 0.6% away. All right, so hopefully this gives you an idea of how well the numbers match up. It's a pretty good approximation, especially when dealing with big numbers. Obviously, the bigger the n is, the better the approximation will be, because when we look at our graph here, these rectangles will get thinner and thinner, and there will be less and less overlap and underlap, and therefore we'll be able to make an even better approximation. So hopefully that gives you a good idea of how the normal distribution works in conjunction with binomial. And oh, the last thing I should mention is that this that we're talking about here with the 1.5 and 2.5 is called a correction for continuity. Okay, so it's when we have something that's discrete, like binomial, something that's continuous, like the normal curve, that we're trying to describe a discrete thing that we then have to consider that whole range rather than just that specific value. Okay, so that's your correction for continuity, and we are done.